Hello dear students, this is grade 11 mathematics lesson on unit 1 further on relation and functions. So today we'll focus on further on relation function. So after revising this lesson, you are expected to realize the concept of relation and functions and determine inverse of a relation and identify whether a given function is even or odd. So let's continue to the lesson. Relation is a set of ordered pairs. What does this mean? Look this one. If we have, take this. If you have this 1, 2, 3, 4, it's a set. But it is not the set of ordered pair. It is a set of single numbers. But if you take this one, R, 1, 2, 3, 4, this it is a relation because it is a set of ordered pair numbers. Okay, so relation simply it is set of ordered pairs. Given two sets A and B, a relation from A to B is defined as any subset of A cross B. For example, if you have A is a set 1, 2 and B, assume it is AB, any subset of A cross B can be a relation from A to B. For example, A cross B can take A cross B to be 1, A, 1, B, 2, A, 2, B. So a relation from A to B, one relation from A to B can be taken as 1, A, or some part from this or any subset of this will be a relation from A to B. So if you have two sets A and B, a relation from A to B is simply defined as any subset of A cross B. A relation on A is simply it is any subset of A cross A. Now let R be a relation from A to B. Then domain of R is this. Is the set of first ordered pair, simply the set x taken from A, says that the ordered pair xy is element of the relation. So the set of first ordered pair we call the domain of this one for some y in B. And the range of R is simply it is the set of the second ordered pair where xy is element of the relation for some x element of A. So now let's see example. Let A is this 1, 2, 3, 4, 5 and R is a relation of xy such that x plus y is 6 and x and y are taken from A. Then find the element of R. We are asked here to find the element of R. The element of R is the relation is just defined by this formula x plus y is equal to 6 and x and y must be taken from this one from the set A. So to list some of the elements of R, if you take 1, if you put 1 here, y must be 5. We have 5 in A. So 1, 5 is one of element of R. And if you take 2, 2 plus y 6, y must be 4. 4 is in A. So 2, 4 is another element. If you take 3, 3 plus 3 is 6. So 3 is in A. So this is another element. If you take 4, 4 plus 2 gives you 6. 4 and 2 are in A. If you take 5, 5 plus 1 gives you 6. But if you take 6, 6 plus y is 6 means y must be 0, but 0 is not in A. So 6 comma 0 is not element of R. So these are the elements of R. From this, you are also asked to find domain of R. The domain of R is simply the set of first ordered pair. Therefore, the domain of R will be a set of the first ordered pair. 1, 2, 3, 4, and 5 are the domain of R. 1, 2, 3, 4, and 5. These are the domain of R. And range. The range of R will be set of second ordered pair. Second order pair 5, 4, 3, 2, 1. That means it is 1, 2, 3, 4, and 5. Therefore, the range is also it is 1, 2, 3, 4, and 5. This is it. Okay. Now let's continue to inverse of a relation. Let R be a relation from A to B. The inverse of R is denoted by this symbol, R inverse. It's read as R inverse. And it is a relation from B to A. And it is given by R inverse is equal to the ordered pair BA, where AB is element of the relation. If AB is element of R, then the element in R inverse is simply changing A and B. So it is BA. And from this you can see that the domain of R inverse is the same as the range of R. From here, the domain of R is this first order pair, and the range of R inverse is second order pair. That's the same. So the domain of R inverse is equals to the range of R, and similarly the range of R inverse gives you the domain of R. Now let's see example for this. Look this one. We have R to be this the ordered pair xy such that y is greater than or equal to x plus 3 and y is less than minus 3x minus 1. Then give R inverse and determine the domain in range of R and R inverse. So to find the R inverse of this, we will have two ways of writing R inverse of this relation. The first way is simply change the ordered pair xy and leave this inequality as it is. So this one is one way of writing R inverse of this relation. Therefore, you'll have this one. R inverse will be, it is the ordered pair yx such that, leave this one as it is. Y is greater than or equal to x plus 3 and y is less than minus 3x minus 1. It's one way of writing R inverses in this form. We can also write in this form. R inverse is equal to this. Leave xy this one as it is and change the variables x and y in the inequality here. So R inverse will be this simply the ordered pair xy such that change x and y here. So it will be this x greater than or equal to y plus 3 and this one x less than, change x and y, x less than minus 3y minus 1. We can also rewrite this in another form like this. R inverse will be the ordered pair xy such that you can solve for y here. Y is less than or equal to x minus 3. When you solve for y, you will have y is this less than or equal to, take 3 to this side, you will have x minus 3. And solve for y to here. So when you solve for y, you will have this one. Y, taking minus 3y to this side, you will have positive 3y. So y is less than, take x on the other side. So minus x minus 1 divided by 3. So it's the R inverse. Okay, now next to this we'll see how to find the domain and range of R and R inverse of this. To find the domain and range of R and R inverse of this relation, we need to draw the graph so we can determine its domain range from the graph. So let's draw the graph of this. To draw the graph, we have this one, y is greater than or equal to x plus 3. So from this, convert this to equation to find the boundary line, y is equal to x plus 3, and prepare a table for this one, x, y. When x 0, take only intercept. When x is 0, 0 plus 3 it is 3. And when y is 0, x will be this negative 3. You will have this one. And the other line, y is less than minus 3x minus 1. For convert this into equation, y is equal to minus 3x minus 1. So take the intercept x, y, when x is 0 and when y is 0. When x is 0, y becomes negative 1. And when y is 0, x will be this negative 1 over 3. So you will have this one, and then draw the graph. So let's draw the graph here. So here, let's take this to be 1, 2, and 3, negative 1, negative 2, and negative 3, 1, 3, 1, 2, 1 to 3, negative 1, negative 2, and negative 3. We have this one. So to draw the boundary line for y greater than or equal to x plus 3, let's use this table. When x is 0, y is t3, we have this point. When x is negative 3, y is 0. When x is negative 3, y is 0, we have this point. The boundary line, it includes the boundary line since these inequalities are equal to. So you'll draw this line and check which part will be shaded, below or above. Taking the origin as a test corner, take 0, 0, 0, put 0, 0 here. 0 is greater than or equal to 0 plus 3. It is wrong. This part is not part of our graph. It is other side. Therefore, the shaded region will be above this line. And then draw the graph for this one, boundary line. When x is 0, when x is 0, it is y is negative 1, this point. And when x is negative 1 over 3, assume 1 over 3 is here. Y is 0, it is this point. So the boundary line is less than. Therefore, it doesn't include the boundary line. Use broken line. This one is the boundary line, y is equal to minus 3x minus 1. This is a boundary line, y is equal to x plus 3. So let's check which part of this line will be shaded. Take 0, 0, put it here, 0 less than 0 minus 1, it is minus 1. 0 is less than minus 1, it is wrong. So this part is not our part of our graph. It will be shaded to this side. So when you shade the lower part, the intersection part of the graph will be upward part and downward part. You will have this one. This part will be the part of our graph. This is our graph, this shaded region. And we have this intersection point. So to find this intersection point, you can add these two, and simultaneously you get this point to be negative 1 comma 2. Negative 1 comma 2. So from this graph, now I can determine the domain in range of this relation. Domain of R is equal to, as you can see, you'll find this region to the left of this point. Since this line is not our part of a graph, this line and this line do not have intersection at this point because this is a broken line. It's not a part of our region. So it doesn't include this part, but to the left of this part will be our domain. This means that this point is negative 1. So the domain of this relation will be x less than negative 1. It doesn't include negative 1 because it's a broken line. This is a solid line. Their intersection is not our part of region. Therefore, the domain will be x less than negative 1. And which is it is? The domain of R means it is the range of, which is the same as range of R inverse. No need of doing or drawing the graph for R inverse. This is the range of R inverse. Similarly, the range of R, as you can see, this region extends to the upper part and lower part throughout y-axis. It decreases down, so we don't have a limit for its range. Therefore, its range will be this all real number. So the range of R is all real number. This is the same as the domain of R inverse. This is it. So let's continue to the next part. Functions. A function is a relation in which no two distinct ordered pairs have the same first element. For example, if you take this one, let's take R 1 comma 2, 3 comma 4, 1 comma 3. If you take this relation, here the first ordered pair is repeated and the ordered pair are different. They are different. The first ordered pair is repeated. So this is not a function. The definition of a function says no two distinct ordered pairs have the same first element. So this is not a function. It's not a function. But if you take this one, 1, 2, 3, 4, 1, 2. Even though the first ordered pair is repeated, these two are not distinct. So this relation means you can just cancel this one. So I can write this in this form: 1 comma 2 and 3 comma 4. So as you can see, not the first order pair is repeated. Hence this will be a function. These two are the same. These two are the same because you can cancel this one. That this ordered pair and this ordered pair are the same. So you can cancel this one and you can reduce this in this form. So since the first order pair is not repeated, this one is a function. Okay, now let's see additional example here. Let R is given to be this one. If you are asked to check whether this one is a function or not, look the first order pair. The first order pair here is repeated, but these two are the same. So you can cancel this one. This will be a function. It will be a function. And let's take this one. Let R is given to be 2 comma 1, 3 comma 5, negative 1 comma 2, 2 comma 2. Is R a function? If you check here, 2 is repeated here. These two are distinct. Therefore, this one is not a function since the first order pair is repeated. Now, let's check this one. Let R is this order pair xy says that x is the father of y. Is it a function? To check this one, we have x here and y here. Here x is a father and children here. Maybe he may have more than one children. So this father will pair with different children. Therefore, father we see 1, father we see 2. The first order pair will be repeated. Because of that, x is the father of y is not a function. Is not a function. Now let's continue. If we face a graph to check whether that graph is a function or not, we use vertical line test. Using vertical line test, a set of points in Cartesian plane is the graph of a function if no vertical line intersects the graph more than once. In that case, the graph will be a function. For example, if you have this graph, if you take any vertical line crossing this graph, this is a function. Since any vertical line crosses this graph exactly at once. But if you take this one, assume this graph, if you take a vertical line or if you draw a vertical line to the graph, it crosses more than once. So this will not be a function. So this is how we use vertical line test. Now next, if f is a function with domain A and range a subset of B, we write f is a function from A to B. If f is a function from A to B is given by a rule that maps x from A to y. This means if f is a function from A to B, this one is A, this one is B. If f is a function from A to B and it's given by a rule that maps x from A to y in B, then we write f of x gives you y. So we write f of x will be this y. A function f from A to B is said to be odd if f of negative x is equals to negative of f of x. If satisfies this, the function will be odd. And a function is even if and only if f of negative x is equal to f of x. The evenness and oddness of a function, we call this parity of that function. Now let's see example. Check whether the following functions are even or neither. So let's take this one, A. Take the function f of x to be equal to the square root of x to the power of 4 plus 1. Is this function even or neither? To check this, first let's determine f of negative x and compare with f of x. If they are equal, even. If they are opposite, it's odd, using the expression previously expressed. So here f of negative x, this equal to negative x the power of 4 plus 1. So this gives you the square root of x the power of 4 plus 1. As you can see, f of x is the same as f of negative x. If f of x and f of negative x are equal, then the function we call it even. Therefore, f of x is equal to the square root of x to the power of 4 plus 1 is even function. It is even function. Now let's see another example here. B, f of x is equal to 1 over x. Is this function even or neither? First, find f of negative x. F of negative x gives you, it is 1 over, in place of x you put negative x. Therefore, from this you can see that f of negative x is equal to negative of 1 over x. This is equal to negative of 1 over x means it is f of x. So, as you can see, f of negative x and f of x are opposite. So, in this case, the function odd. Therefore, f of x is equal to 1 over x is odd function. It is odd function. If you see this one, f of x is equal to, take x plus 1. If you take this, let's find f of negative x will be equal to minus x plus 1. So, these two functions, f of x and f of negative x, they are not equal. Even they are not opposite. The opposite of x plus 1 is negative of x minus 1. They are not opposite, they are not equal. So, this is neither even nor odd. Therefore here, f of x is equal to x plus 1 is, it is neither odd nor even. So this is it. Now let's continue to the other part. Types of functions. The first one is this, a power function. A power function is a function which can be written in the form of f of x is equal to a x the power of r, where r is rational number and a in r is a fixed number. So f of x is equal to a x the power of r is this, a power function. And here, a power function f of x equals to a x the power of r, it satisfies this property. F of xy is equal to f of x times f of y if the coefficient this one, if this is 1. Please check this one by yourself. If a is 1, f of xy gives you f of x times f of y. Otherwise, it doesn't give you. So, for example, from this set, which one satisfies this property? F of xy is equal to f of x times f of y. A, f of x is equal to the square root of x. B, f of x is equal to 2x the power of 1 over 4. Which of these two satisfy this property? You can check by putting f of xy, but easily this is a power function, this is also a power function, but the coefficient of this power function is 2. So this doesn't satisfy the property f of xy is equal to f of x times f of y. But this one can be written in this form, x the power of 1 over 2. So it's a power function with this coefficient 1. So it satisfies this property, f of xy is equal to f of x times f of y. Now the sine function, it's read as sine of x. It's written as secant x, and it is defined by, this sine function is defined by, simply it is 1 for positive numbers, 0 for 0, and negative 1 for negative numbers. The sine function is defined in this form. Or this is equivalently written in this form, absolute value of x over x for x different from 0. Absolute value of x over x for x different from 0, it gives you 1 for positive number, negative 1 for negative numbers, and in addition to this we have this one for x equal to 0, it is 0. Therefore these two are equivalent. So if you are asked, for example, to find what is the sine function of 2 or secant of 2, in this case its value it is 1 for any number, greater than 0, the sine function takes 1. If you are asked the sine of 0, the result will be it is 0. For the row it is 0. And if you are asked what will be the sign and function of negative 10, for negative numbers it gives you negative 1. The sign and function is negative 1 for x is less than 0. The greatest integer function is denoted by this one. F of x is equals to the greatest integer of x. This is defined as it is the greatest integer less than or equal to x. The greatest integer less than or equal to x. For example, what is the greatest integer less than or equal to 3.2? Integer, for the number is integer. So the greatest integer less than 3.2 is it is 3. And if you are asked what is the greatest integer less than or equal to 2 is this 2. According to the definition, the greatest integer less than or equal to, you can take 2 if it is integer. If it is not integer, you take a number less of it. Therefore, here since 2 is integer, you can take 2 itself. Therefore, the greatest integer less than or equal to 2 is it is 2. And if you are asked to find what will be the greatest integer less than or equal to negative 2.5. The greatest integer less than or equal to negative 2.5. Here it is negative 3. So this is a definition of greatest integer function. Now let's see classification of functions. The first one-to-one function. A function f from a to b said to be one-to-one or injective if and only if each element of the range is paired exactly with exactly one element of the domain. Or in other words, if f of x1 is equal to f x2 implies exactly x1 is equal to x2, then for any x1 and x2 in A, then the function we call one-to-one function. And to check the graph whether it is one-to-one or not, we use a horizontal line test. A function f from A to B is one-to-one if and only if any horizontal line crosses the graph at most once. So let's see example for this. Example 1. Take this one. F of x is equal to x plus 1. It's f of x defined from real number to real number. Assume it's defined from real number to real number. And it is f of x equal to x plus 1. Check whether it is one-to-one or not. To check whether this one is one-to-one or not, simply you can draw the graph, you can check horizontal line test, or you can apply this one. So let's check solution. F of x1 is equal to f of x2. This implies f of x1 means simply it is x1 plus 1. And f of x2 means simply it is x2 plus 1. These two cancels out. You'll have x1 is equal to x2. So since f of x1 is equal to f of x2 implies x1 is equal to x2, this function is one-to-one function. Therefore f of x is equal to x plus 1 is one-to-one function. It is one-to-one. It's one-to-one function. By the way, you can check by drawing the graph and using horizontal line test. If you draw the graph, if x equals to x plus 1, you'll have this one. If you draw any horizontal line, that horizontal line crosses this graph exactly at 1. Therefore, this is a one-to-one function. Now, let's see second example here. Let's take f of x is given by x squared, where f is defined from real number 2, a number greater than, let me write in this form. It is f is defined from real number 2 0 to infinity. Say that f of x equal to x squared. To check whether this 1 to 1 or not, you can draw the graph, or you can apply this formula f of x1. Using that, f of x1 is equal to f of x2. This implies f of x1 means it is x1 squared. F of x2 means this x2 squared. So to find the value of x, put both sides under square root. Under square root, you will have absolute value of square root of x squared is absolute value of x. So it is x1 under absolute value, and absolute value of this x2. So when you solve this, you will have this one. x1 is equal to plus or minus x2. So as you can see, f of x1 is equal to f of x2 doesn't imply exactly x1 is equal to x2. It may be x1 is equal to x2 or x1 is equal to minus x2. Because of this function is not one-to-one function. Or you can check this using graph. If you draw the graph, you will have this one. And if you check a horizontal line, it crosses the graph more than once. Because of this, f of x is equal to x squared is not a one-to-one function. So let's continue. On to functions. A function f from a to b is onto or a surjection if and only if the range of f is b. So for example, let's take this one. F is a function from the set of real number to real number defined by f of x is equal to x squared. To check whether this one is onto or not, simply you have to determine the range of this function. If the range of this function gives you this one, the function will be one-to-one, otherwise not. So the range of f of x, when you draw the graph, its range will be is greater than or equal to 0. So its range is from 0 to infinity. This not gives you real number. So because of this function is not onto function. Okay, this is the first example. Let's take second example. If you make this one in this form, f is a function from real number to 0 to infinity defined by f of x is equals to x squared. In this case, the range of this one gives you this. Therefore, in this case, this will be a one-to-one function. For this case, one-to-one. Let me give you third example here. Look, this one. This is a. It's a function from a to b. And you have this one. Here it is 1, 2, 3. And we have here it is a, b, c, d. One is mapped with a, 2 is b, 3 with c. Is this one a one-to-one function? It's not, because the range of f or it's not b, it is a, b, c only. D has no pre-image. So because of this is not onto function. It's not onto. So now let's continue to the other part. One-to-one correspondence. A function f from a to b is said to be a one-to-one correspondence or a bijection if and only if f is 1 to 1 and onto. It must satisfy both. If it is 1 to 1 and 1 to, in that case, a function is said to be 1 to 1 correspondence. If you take this one, let f is a function from real number to real number defined by f of x is equal to x plus 1. Since we have checked, f of x plus 1 is 1 to 1. 1. F of x is 1 to 1 function. So the other one, to check ontoness, the range of this must be this one. Yes, the range of f is, the range of f is this, it's a set of real number. So gives you this one, so it is onto. It is onto. Since it satisfies 1 to 1ness and ontoness, the function is this 1 to 1 correspondence. Therefore, f is 1 to 1 correspondence. F is 1 to 1 correspondence. This is it. To summarize what we have seen today, 1, we have seen about relation. Relation is set of ordered pair. And second, function is a relation in which no two distinct ordered pairs have the same first element. And a function from A to B is said to be odd if f of negative x is equal to minus of f of x. It is even if satisfies f of negative x equals to f of x. And the function from A to B is said to be 1 to 1 or injunction if and only if each element of the range is paired with exactly one element of the domain, or if it satisfies f of x1 is equal to f of x2, implies x1 is equal to x2. In that case, we say the function is 1 to 1. A function f from A to B is said to be onto or surjection if and only if the range of f it is B. And the function f from A to B is 1 to 1 correspondence if it is both 1 to 1 and onto. And please do exercise 1.1 on page 5, exercise 1.8 on page 23, and exercise 1.9 on page 25. So this is all about today's lesson. Until next lecture class, goodbye.